Hello, everyone. I'm Madi Tavakkoli. I'd like to talk to you about a couple of technologies for mobility assistance. So I'll talk about a wheeled mobile manipulator and also about a lower limb exoskeleton, some of which we have developed and some we are just using to control. So the patient group for, in terms of mobility assistance is, people who have suffered from, for instance, a stroke, a spinal cord injury, multiple sclerosis, cerebral palsy, and things like that. So some sort of disabling event that does not allow them to walk normally, or just older adults who are in home care or in senior homes and in need of assistance. So what I'd like to do is to talk about assistance being provided by a wheeled mobile manipulator, the one that you see on the bottom left, and also adaptive gait planning using a lower limb exoskeleton, as you see on the right-hand side. And also at the same time, how do we adapt to the gait pattern of a user while ensuring balance? And then I'll talk about using AI for personalization of the walking pattern of the user. So let me start with using a wheeled mobile manipulator for mobility assistance. We call this a smart robotic walker, and we view it as a kind of a hybrid between a cane and a walker. So this is for independent living of seniors, and what we'd like to do is to have some sort of intention detection to be able to estimate what the user wants to do and assist them in doing so, and also adapt to the locomotion pattern. So what you see here is basically just a Kinova robot that we have mounted on a wheeled mobile base. That's an omnidirectional wheeled base. And then we have attached something like a bicycle handle to the end effector of the robot so that users can grab onto it and with proper control use it for walking. So the robot is supposed to guide and assist them in walking. And also, maybe with control, we can do fall prevention. So this is for the assistance, and maybe even it can be used for rehabilitation. So really, the main thing here is that we've attached basically force sensor, and the force sensor allows you to measure the forces in 3 directions and even torques as applied by the user on the handle. So what we'd like to do is use the estimation of these interaction forces between the user and the wheeled mobile manipulator in order to understand what the user wants to do and then assist them in doing so. So what we want is basically if the user starts applying some large Fx, it means that the user wants to move forward, the robot moves forward. And if the user stops applying some large Fz, it means that the user wants to use this as for gravity support, therefore the robot should not move that much and act like a cane. So sometimes act like a walker and sometimes act like a cane. This is easy to do. We just need to do some sort of impedance control or admittance control, which you see is what's done here. So if the user applies a large Fx, then the admittance will grow, basically, meaning the impedance will go down and the robot will loosen up and allow the user to push it. And as soon as the user starts applying some large Fz, then the robot will slow down. So it becomes like a stable support for leaning onto. So this is the first part, the compliance control. And then the second part is once we enable this, once we have this variable impedance control, enabling the user to use it for guidance or for gravity support, then we want also the robot to adapt to the walking pattern of the user so that the user has to apply less force, so that the user doesn't have to apply too much force by the upper limbs, and that becomes another issue. So we have used cooperative dynamic movement primitives, and I won't go into the detail because this gets complicated pretty soon, but really the idea is that attractor, that target point for the DMP is a function of how much force the user has applied in the forward direction. The higher the force, the farther will be the attraction point that this path planning algorithm is trying to get the robot to. And so that is found out in one gait cycle. In the next gait cycle, it's cloned while allowing for some variation so that the user has to apply a smaller force. And we have added some sign function here for fall prevention. So in terms of results, let me show you first the result of variable impedance control. Really, the main thing here is that if you look at the conventional approach, this is the green, this is the red. So this is the forward position of the robot versus time. And this is our proposed approach, the black one. What you see here is that when FZ is big, the robot slows down and kind of stops in that position, and the velocity goes to 0 or becomes very small, so that the user can lean onto the robot. And what you see here is that when the force is large, when the downward force is large, then the user has the robot is basically stopped for the user to use it as gravity support. And what you see here on the left-hand side is that the user, thanks to this cooperative DMP, has to apply a smaller amounts of force to push it forward. We identify what the user's intention is, and then we help the user get there with a smaller force applications. So this kind of ongoing work, but I just want to show you this video. So it's pretty easy to push the robot forward. We are not showing all scenarios here, but it has that element of variable impedance control and also cooperative DMP. So now that we built this system, we thought, why don't we kill two birds with one stone? Why don't we use this not just for mobility assistance, but also for object manipulation support? Because seniors require some help with lifting heavy objects. So let's say you need two people, let's say, to lift an object. Why can't there be a helper showing the robot through demonstrations, hands-on demonstrations, what the task is, and then this task can be carried out in the absence of the helper by the main user later on. So this is basically learning from demonstration, where the robot observes and learns from a human's actions and then reproduces those actions in future iterations of the task in the absence of that helper or demonstrator. So that's what we have done here. So what you see on the left-hand side is the demonstration, and the right-hand side is the reproduction. So first, the demonstrator is there showing the robot what needs to get done, and then in the absence of the helper, the robot learns that behavior and reproduces it. Now, something interesting is that this combination of the wheel-based and the manipulator is a redundant robot, and therefore you can use knowledge space control to reconfigure it, control the internal motion such that the robot has maximum force exertion capability in the direction of gravity for moving heavy objects. So this is the first piece of work where we use this wheel mobile manipulator for mobility support and object manipulation support. Now, going to lower limb exoskeletons, I'd like to talk to you about how the exoskeleton can adapt to a user's gait patterns and what the user requires by properly shaping the locomotion trajectory. So the gait pattern changes from one person to the next person. It even changes for the same person when the person becomes fatigued. Most exoskeletons dictate one predefined and fixed trajectory to for the gait, and do not allow the user to change it. So we thought about how we could change the gait pattern depending on what the user wants. And so how can we identify the human intention in a few ways: brain computer interface, user input, other forms of detection. We decided to go with physical human-robot interaction. So can we use physical human-robot interaction in terms of the forces that the user uses to push the exoskeleton faster or slow it down as cues to reshaping the trajectory for the gait? So that's the main idea. Now, the next question is, okay, if you change the speed of walking, let's say, through paying attention to the physical human-robot interaction, what happens to the stability? So if you move faster, also you need to think about keeping balance and keeping the exoskeleton and the person stable and not falling. So that's the second piece that we worked on, that's using divergent components of motion for walking balance. So the intelligent control method will have two parts. One is using these central pattern generators for adaptability of the exoskeleton step length and walking speed to the gait pattern of the user, or what the user needs and feels comfortable with. And the second part is enhancing postural stability to ensure that there is balance, and that's for basically safety. So if you look at trajectory generation work, it's either mostly DMP or these central pattern generators. DMPs, at least the discrete ones, the point-to-point DMPs, do not allow, they're not built for capturing rhythmic motions, and they're good for generating general motion trajectories. But central pattern generators, or CPGs, are specific to rhythmic motions, and therefore we chose that. So humans have basically central pattern generators. They're a group of neurons that produce pattern and rhythmic output for walking. There's artificial CPG, which is basically a sum of sinusoids, as you see at the bottom of the page, for creating time-continuous rhythmic motions for different joints of the lower body. So now, the idea is to change the amplitude, the frequency or phase, and this offset value in the artificial CPG in order to adjust to what the user wants to do. So that's the problem that we're going to look at. How can we change the amplitude, the frequency, and the offset, which basically an offset is the equilibrium position where the start and end angle for each joint is. How can we change them depending on the physical human-robot interaction between the human and the exoskeleton? So the goal is to use this physical human-robot interaction torque as the user's intention. So that's what we are going to use, and then somehow modulate amplitude, frequency, and equilibrium based on how much force or torque the human applies on the exoskeleton, either in the forward or in the reverse direction. So what we did, and this is the kind of a neural network, we use the neural network to estimate how much force the user is applying on the exoskeleton when he or she is wearing the exoskeleton. So that's basically based on some trained data, we found that. Once we found that torque, which had to be estimated because we do not have such a sensor on the exoskeleton, then we threw that into these formulas and calculated the interaction energy. This is what we call interaction energy based on this interaction torque, and also the total torque based on the interaction torque across time. So then the way this works is that the CPGs are adapted using equations that I'll show based on these two inputs, the interaction energy and the torque, basically, that are calculated from the torque of human-robot interaction, which is the output of the neural network that I talked about. So how does this exactly happen? Once we have the interaction torque and calculate this energy and torque, how does the CPG change? So that energy term changes the amplitude and frequency of the motion, while the torque changes the equilibrium position. So this is the choice we made. So these are basically a set of differential equations that give the frequency, amplitude, and that offset over here in the CPG, which is the planned trajectory for each joint. So there are some terms that kind of saturate how much the torque, how much the amplitude or equilibrium can increase. And there is also a similar term for the frequency. But really the main contribution was here. We added energy or torque, okay? So if the human is applying positive energy, the human wants to go faster. So we increase the amplitude of the step length, basically, and also we change the frequency of walking, which is how fast you walk, the velocity of walking. And also the torque. If the human is applying forward torques, then the human is wants to go faster, so the angles have to increase. And so this is really the contribution that we made in this work. So here are the some videos that you see. Now, what you see in these videos, if you pay close attention, at the beginning, it's very difficult, relatively speaking, for the human to push the exoskeleton to go faster. But after a few seconds, it becomes easier. Like if you are wearing the exoskeleton, you will see that that's a noticeable difference, that the exoskeleton will it'll become easier for you to push it forward because it has used the past interactions that the human has had with the exoskeleton to increase the amplitude and increase the speed of walking. So this is, in both cases, the human wants the exoskeleton to go faster. So if you look at the results, you have it for the right hip, the blue, and the left hip, the green. So as you see, this is the interaction energy. So the human put more energy for going faster on the right hip. Therefore, the amplitude or the step length moved up high, faster compared to the left hip. Okay, but after you pass some threshold, then the rate of increase saturates so that the step length does not become too much. And this is basically how that log function that I showed you created negative terms that discourage increasing the amplitude too much. And this is the result for the frequency. So overall, you see that the frequency of walking increased over time as the human started putting more and more energy. These are basically the trajectories for the right hip and left knee, and basically this shows the effect of position control. So now we have done adaptation of the gait pattern to the user's needs. One problem is that we use a neural network to identify or estimate the human-robot interaction. Neural networks are always going to generate some sort of prediction, but sometimes they're unqualified for the prediction that they are making because they have not seen such a thing in the training data. How can we use neural network outputs with any degree of reliability? Because this is a safety critical system. So medical robots are safety critical systems. When we use AI as part of decision making, we need some sort of safety analysis. Deep learning does not provide any safety guarantee about how reliable the performance is. So how are we going to use it? What we did was we learned from the domain of uncertain analysis for deep networks and replaced that neural network by a random forest regression model, and then did this out of distribution detection. So we detect if the input sample that we are getting is significantly different from the training test. And if so, we attach a low weight, low confidence to the changes that are going to happen to the CPG. So that's really the main thing. So we have the same CPG, but we have this confidence factor. And confidence factor is at most 1 when we are fully confident, or 0. And this dictates how much we listen to the predictions made by the neural network. Now, how does this out of distribution or uncertain analysis approach work? Is that it's a combination of KL divergence and this distance. KL divergence looks at the distance between the distribution of the label data and the predictions during training, and the other distance looks at the test and training set distance. So if the input is substantially different, then the distance will be high. And this is examples where the input was significantly different from what the network was trained for. And in these cases, like these two cases at the end and these cases early on, we again attached a smaller gain to that change that interaction energy or torque was going to make in the CPG. So the value was not significantly updated when the confidence in the prediction of the network was low. The next thing that I'd like to talk to you about is maintaining balance in walking under adaptive gait planning. So for user safety, it's important to not only once we change the speed and step length, we also have to change the upper body position so that the person does not fall. As you go faster, you move the center of mass of the upper body forward to maintain balance. So how can we do this? We used DCM analysis, which has been used previously for bipedal locomotion, but we used it with some extension for human exoskeleton system. So we want to give the velocity of walking to it and then get the desired upper body position, and using the hip joint of the exoskeleton, move the person forward as the person goes faster to maintain stability. So previously in the DCM, they've used for the lower leg, they've used an inverted pendulum and a flywheel model for the hip. We changed it and used the 4-body model. So 1 body for the stance leg, 2 for the swing leg, and 1 for the upper body. And then if you look at the position of the center of mass, it is the sum of C plus D. So the sum of C plus D will be the center of mass. This is the convergent component, because at the steady state, this will converge. This will become 0 and this will converge. But this is the divergent component of motion, which has this dynamic. So for a stable locomotion, it's important that this DCM, this zeta, reaches at the end of the step some desired value. What is that desired value? It is the summation of the position of the center of pressure of the stance leg, coming, for instance, from the pressure insole, and some offset, which is like this. So we calculate where the DCM should be at the end of the step, and therefore it's a simple optimization problem. What is the minimum torque that has to be applied to the hip joint so that the divergent component of motion reaches the desired value for it as calculated according to what I discussed at the end of the step. So this is done, and therefore we basically have now a few levels. We have a position control at the low level. We have a CPG, which is our motion planning, one higher level. And before that, we have this DCM that changes the position of the upper body for stability. And if you look here, at the end of each step, for each right and left limb, the DCM reached the desired value under proper DCM control, but without it, it did not. And if you look here, basically what this is saying is that as the human goes faster, then the upper body is moved forward so that balance is maintained. So far we used CPG for adjusting the amplitude and frequency, and we also used the HRI torque for changing the equilibrium point. This was the adaptive part. Then we added the robustness analysis or uncertainty analysis to only use neural network predictions when we have high confidence in it. That was one change to the CPG. And then we added one more layer, which is DCM analysis for maintaining balance and ensuring that the upper body position is appropriate for viability of walking and that the center of mass is within the support base. So we've talked about adaptivity, postural stability, and personalization. Very quickly, just my last few slides, I'd like to talk to you about personalization using reinforcement learning of the gait. So when we change the CPG, we use energy and torque terms multiplied by some fixed gains. Those were fixed gains that change the amplitude and frequency. Those gains are going to be different for every person. From one person to the next, the amount of muscle they have, the body build is different. And even for the same person, the muscle performance changes with fatigue. So we need to have a way to change those gains according to the needs of the person in real time and not have them fixed. So for that, we use reinforcement learning. And reinforcement learning is going to personalize that gain for each person, and even as the person gets tired, change it. And how it's going to do that is it's going to have a reward function that looks at, okay, I have an amplitude and I have a frequency of walking. I don't want them to change too much. But if the user struggles too much to change them or too many times to change them, obviously they need a higher gain, right? So that's the way. So this reinforcement learning reward function is going to penalize repeated try attempts by the user to go faster, for instance, or go slower. So if you try too many times, it means you're struggling. Therefore, we just amp up the gain for you in changing that. So this is how the results, at the top you have without reinforcement learning, and at the bottom you have with reinforcement learning. You see that the convergence to these desired values happen much faster compared to no learning for the case of reinforcement learning. It's a matter of 10 to 20 seconds to converge, but about over 120 seconds to converge without that. So this is the kind of videos. So right-hand side is without reinforcement learning, and left-hand side is with reinforcement learning. At the top, you want to go faster, and at the bottom, you want to go slower. So this adaptation happens, again, between 12 to 25 seconds for the case of reinforcement learning, but about 2 minutes for the case of no reinforcement learning, because the gains were fixed, and so there is no adaptation there. And with that, I'd like to finish. So I talked about mobility assistance. We used a smart robotic watch. It's a built mobile manipulator for both mobility assistance and object manipulation. And mobility assistance includes acting as gravity support, for gravity support, depending on in which direction the user is applying forces. I talked about adaptive central pattern generators that change the amplitude, frequency, and equilibrium point of the trajectory based on the human-robot interaction. And then later, we made it safe by looking at the confidence of the prediction of the neural network and using that as a gain. We also wrapped another layer around it and ensured that we can maintain balance as the velocity and step length changes. And finally, it was about personalizing the locomotion trajectory by accommodating changes in muscle lengths, muscle strengths, and also variation of muscle strengths between users. So we talked about adaptation, safety, balance, and personalization. Thank you so much. I have to thank all my collaborators and students, past and present, that have contributed to this work.